All right, so one more problem to go over here before our test on Thursday. So you asked to see a curve sketching. So here's the problem. Go ahead and pause the video and write that down. These are all the things that we need to find. Domain, x and y intercepts, vertical and horizontal asymptotes, critical points, min, max, point of inflection, concave up, concave down, and then determining the end behavior. So before I do all of that, I know I'm going to have to do my derivatives eventually, so I'm just going to start off by doing that. And I can reference them later. So first derivative, low x to the third, the derivative of the top, so low d high 2x minus 5, minus high d low, so x squared minus 5x, minus 6. Derivative of the bottom is 3x squared. And this is all over the denominator squared, which will give us x to the 6th. Cancel out what we can. Cancel out what we can before we go through and do any simplifying. So the smallest x's that we have are x squared. So that's gone. This will be a 4, and this will just be a 1. So let's do that before we do anything else, so we don't have to worry about, simplifying later. We'll just simplify there. It makes the math a lot easier in the middle here. Multiply this out. So we get 2x squared minus 5x minus 3x squared plus 15x plus 18, and again our denominator is x to the 4th. And one more step here for the first derivative. We will have negative x squared plus 10x plus 18 all over x to the 4th. Okay, now I'm going to leave this space over here because if you look at this, you recognize, all right, this is not a nice factoring problem. If that middle would have ended up being an 11, we'd be set. Well, no, because that negative would change that. But anyway, it doesn't factor nicely either way. So we're going to have to use quadratic formula. And I do want to point out that this will be on your calculator portion of the test. I know I'm asking you to graph a function using on the calculator portion. You can use your calculator to verify that. But really I'm looking for all the parts. If you have all those parts correctly, sketching the graph will be a very minor part of this problem. This has a lot of different parts, so I'm going to save this step right here to do that. So you will be able to use your calculator for finding that, for finding the zeros there when we get into the critical values. So now for our second derivative, again, low, x to the 4th, the derivative of the top is negative 2x plus 10 minus high, negative x squared plus 10x plus 18. D low, so the derivative of the bottom is 4x cubed. And this is all over the denominator squared, which will give us x to the 8th. Oops. Yeah, where's my eraser? There we go. Okay, let's try that again. X to the 8th. There we go. All right, so I'm gonna jump right to the final answer here. You simplify and do everything just like the last one, but I'm just gonna jump. So do that simplifying and then see what you get. I got 2x squared minus 30x minus 72. So that's what you should get there. You could divide a 2 out if you wanted to make the numbers smaller for your quadratic formula, but it doesn't really matter. We're going to use our calculator. So I just left it like this. You get the same answer either way. Doesn't really make a difference, okay? So let's go through all of these different parts here now. So let's see what we get. All right, first up, the domain. From our original function, the only thing we cannot use is 0. So the domain here, negative infinity to 0, that's a terrible infinity, but you get the idea. And then 0 to positive infinity. Okay, next, x-intercepts. What makes that numerator 0? So we get x minus 6, x plus 1. So we have a positive 6 and a negative 1. But remember, we want to write these as points. So 6, 0, and negative 1, 0. Okay, those are your x-intercepts. There are no y-intercepts, and one thing you want to make sure you do here is actually say that. Don't just leave it blank, because that means you didn't do it, but verify that there are, or just state that there are no y-intercepts, or if there are no x-intercepts or something, just say that, like just say none. Vertical asymptotes. What makes the denominator 0? Or in this case, we just end up with 0. Again, vertical asymptotes need to be written as an equation. Horizontal asymptotes need to be written as an equation. So y equals, again, we look at our 3 cases. If we have a bigger power in the denominator than we do in the numerator, then that means this is going to 0. Now, I'm going to jump down to the end behavior, because the end behavior comes from your horizontal asymptotes, but you just have to show what happens. So the limit as x approaches negative infinity of this function would be 0. And the limit as x approaches positive infinity of this function is also 0. Okay, and again, that just comes from your horizontal asymptote. If you end up with a slant asymptote, then you would have to verify, or show me which of these is negative. Does the negative infinity give you a negative, or the positive infinity give you a negative? Otherwise, your horizontal asymptote would be 0, or it'll be some number, right, if the highest powers are the same. Okay, critical points. This is what makes the first derivative 0. So I, again, already did this here. If we set this equal to 0, again, that's where the numerator is 0. And we need to plug this into our quadratic formula. So this is what your quadratic formula should look like. Negative 10 plus or minus the square root of b squared, so that's 100, minus 4 times a is negative 1, and c is 18. This is all calculator work. I will jump straight to the answer once I put this down here. All of this divided by 2a, which is negative 2. Okay? So the two answers, oops, right click, sorry. The two answers that you get here, come on, thing. All right, the two answers you get here are negative 1.557 and 11.557, okay? Those are your two critical values. Now, you can plug them into your calculator to get the y coordinates for your critical points. But again, like I said, I already have this done, so I will just write them down. Let me see here. Negative 1.557, comma, negative 1.115. There's one of your critical points, and the other one is 11.557, comma, 0.045. Again, make sure that you're plugging those in your calculator and you're getting those values. If you're not, let me know. I could have very easily made a mistake, just the same as you guys make mistakes. So just let me know if you do not get those values. Now, we need to know which of these is a min and which one is a max. So from here, we would have to plug this into our table. Before I do that, though, before I make up my table, I'm going to do the point of inflection. I'll just put all of this stuff into one giant table. Actually, you know what? I'm not going to do that. I changed my mind. Just because there's so many decimals that if I do that, we're going to end up with a huge table, and I don't know if we'll fit that in there. So let's see what we get here. Okay, so this problem we do not need to do a table because we already have our critical points, so we already know which one is the highest and lowest, so we don't need to do a table for that. So the minimum point is just the lowest point here, which is the lowest y value. Now this is going to be like a local min, it's not an absolute min, and you'll see when we get into the graph why that's not the case. But our local min will be this point, negative 1.557, negative 1.115. And then the max is going to be the other point because that's your highest value. Even though it's a small number, it's just a positive number. So 11.557, 0.045. That would be your max. So we don't need to do a table for that because we already have the y values. We know which one is the highest and the lowest values just from the y values there. So point of inflection. If we come up here, again, use your quadratic formula here for the numerator. Let's plug that in. We get negative b, so 30 plus or minus the square root of b squared, so 900 minus 4 times a times c. All that's under the square root, all over 2a, so 2 times 2 gives us 4. So again, plug that in your calculator. What you end up getting here are 17.105 and negative 2.105. Okay, and in all of these cases, your decimals should be the same. You just end up with different numbers in front of the decimal. So you can see that in the other one we got 557 and then 105 for this. So, but again, those are the x-coordinates of the points of inflection, so we need to find the y-coordinates. You're going to take that and plug it in, and again, I already have it done, so if you want to pause the video and plug them in, you can, and then check and see if you have it correct. So 17.105, the y-coordinate that goes with that is 0.040, so pretty close to that one. And the negative 2.105, the y-coordinate there is negative 0.960. All right, now when we do the concavity, we do need to have a table for this, so we need to see what makes this concave up, where is it positive, where's the second derivative positive, and concave down, where is the second derivative negative. So in this table, we have, let me move this down so it doesn't end up running into those answers. So the x values, now remember, in addition to our x coordinates for the points of inflection, we also have to include 0, so we have to include any vertical asymptotes as well. So just keep that in mind when you're making up your tables, that it's not just the points of inflection or your critical values, it's also whatever makes the function undefined. So in my table, I'll show you the values that I used, but we needed our negative 2.105. That gave us a 0. We're looking at values for our second derivative now. And then we need to have 0 in here, and that gives us an undefined, so we'll just X that out. And then we needed 17.105. All right, and then we need to find some values around this. So what I used in my table, I used a negative 5, I used a negative 1, I used a positive 5, and a positive 20. So these will give us some numbers that we can use. And again, we're going to plug this into our second derivative. So come back up here. We're going to plug this in here to determine where is it positive or negative. We don't need to know the number. We just need to know positive or negative. So you can go ahead and do that for each of these values and see what you get, and then come back and see if you got the same thing. So for negative 5, I got negative. Negative 1, I got a positive. 5, I got a negative. Oh, I forgot to fill in, this should be a 0 also. And then 20, I got a positive. So again, like I said, typically this will change every other one, negative, positive, or positive, negative. Typically that's what that looks like, but not always, just typically. So anyway, now we know where it's concave up. So let's fill in those values. So it's concave up wherever the second derivative was positive. So between negative 2.105 and 0, where the vertical asymptote was, and then also from the 17.105 to infinity. And then it was concave down all of the other places, so negative infinity up to that negative 2.105. And then beyond, and between 0 and 17.105. Okay, so now we have all of our information here. We'll take this and put it on a graph. So I'm going to try and fit that over here and just kind of get a general idea of what this graph would look like. Okay, so my graph will be in blue, and I'm going to put my asymptotes in red. So we have a horizontal asymptote at 0, which, remember, your graph can cross through horizontal asymptotes, it just cannot cross over vertical asymptotes. So we have a vertical asymptote also at x equals 0. So for my, let's start with the x-intercepts, negative 1, 0. So here we go, negative 1, 0. We'll put that right there. Call this negative 1. And then 6. 1, 2, 3, 4, 5, 6, 0. We got an intercept there. No y-intercepts because we have a vertical asymptote on the y-axis. So the critical points are where the graph is its highest or lowest. Again, we're talking about local, not absolute, max or mins. So negative 1.4, we'll just call it negative 1.5 roughly. We had a minimum. So let's just say, let's stretch this out a little bit. We'll call that negative 1, and we'll call this 1, just because our y-coordinates that we're dealing with here are all right around the area of, negative 1.115 is the lowest. If we just kind of look ahead here, that's about a negative 1. We're pretty much right in that area. We will have to kind of stretch this out to get 17 for our critical value, but we'll worry about that later. So let me try and slide this over. Okay. So we have a minimum at the negative 1.1, so we'll just say that's right about there. Negative 1.5 on the x-coordinate, negative 1.1 on the y-coordinate, so somewhere in that area. And then we had another critical point at 11, which actually I'm going to change this. I'm going to say that these are increments of 2 over here, so that way we can fit everything up here. So let's say 2, I'll write these on here, 2, 4, 6, 8, 10, 12. That'll help us when we're doing this. So we have an x-intercept here at 6. I'm just going to change that, change the numbering there on my positive x-axis. So what do we have here? 11.555 or 557, and then 0.04. So that's really close. So I'm just going to say that's somewhere in that area. Now that's the max. So again, I kind of like to look at what's happening around that and put that together with the horizontal asymptote. So if I'm looking over here, this is my minimum value. It has to connect with this point here at negative 1. So I know right here I'm going to have this graph looking something like that and going up forever. I also know that when I continue out here to negative infinity, it's getting closer to 0. So since this is the minimum, it's going to come up and then kind of run along the negative x-axis. Now, it's not going to cross over because we would have another x-intercept, so it's just going to run very close to it. So that's going to look something like that. Over here, I have a max right here, and then it's going to cross through my point at 6 and go down. And then since the, if we look at our concavity, we know that everything after 17, where we would have our point out here at 17 somewhere like here, this changes to concave up. So there is a slight change in this, like this would be kind of going up, so that would be concave down. And it's very difficult to see what's actually happening there, but we know from the math that it does have a slight upward curve there after this point of inflection that would be somewhere in that area. So that's a general idea of what the graph would look like. So that's pretty much what I would be looking for these type of problems. Now, if you actually graph this on your graphing calculator, this is what it would look like. And you can see here that when you get out to the end, it looks like it runs right along the x-axis. But that's basically just because it's so close to the x-axis. I mean, the highest it is 0.04 something. And then it continues to get closer to 0 as you go out to infinity. So zooming in at where this looks right now, you can't even tell. That's why I made my highest point 1 and kind of stretched out the y-axis when I did the graph there. So just look at the numbers that you have and use that to determine how you want to label your y-axis or x-axis, and then just kind of go from there. So, but there you go. That's all the different parts that we're looking for on a curve sketching problem.